So as we continue, the diagram of pressure distribution for the free earth support method for penetration of clay, its pressure diagram above the dredge line is similar to what is shown in figure 9.10 previously. So the net pressure distribution below the dredge line from Z, which is equal to this value, is sigma sub 6. This one, this sigma sub 6 is equal to 4C sub prime, or this expression. For static equilibrium, the sum of the forces in the horizontal direction is equal to this P1 minus sigma sub 6 times D equal to F. So of course P1 is the area of the pressure diagram in ACD, and F is the anchor force. This is our F, which is our anchor force. So taking a moment about point O prime, our equation will be this one. And it can be simplified to this expression, and we can get our theoretical depth of penetration from this equation. So the maximum moment in this case occurs at a depth in Z is greater than L1 and less than L1 plus L2. In the depth of zero shear, we can have our maximum moment. So a moment reduction technique similar to that for anchor sheet pile penetrating into clay has been developed. Of course, it was discussed by Ro. This technique is presented in the following notation. You have to identify your stability number using this equation. And for the non-dimensional wall height, you have your alpha, which is equal to this equation. And you have to get the flexibility number, Rho. And you have to identify your MD, the design moment, and Mmax, which is the maximum theoretical moment. So we have here the steps for the moment reduction for using this figure 9.29. So basically, you have 5 steps. You have to identify your H prime, which is actually equal to this equation. Identify your alpha prime, determine your stability number. Once you have your stability number and alpha, you can have now your MD over Mmax from this figure 9.29. And of course, you have to follow step 1 through 9 as outlined in the previous discussion for sheet pile walls penetrating a granular soil. So sample problem using figure 9.28. So using this figure for our sample problem, our L1 is 3 meters, L2 is 6 meters, I1, small L1 is 1.5. You have to identify your gamma is 17 kilonewton per cubic meter, and saturated one is 20 kilonewton per cubic meter. T prime is 35 degrees, C is 41 kilonewton per meter squared. You have to determine the theoretical depth of embedment of the sheet pile wall, and you have to calculate the anchor force per unit length of the wall. So for this one, we have our case of A. We have to determine our case of A and case of P. Our case of A is 0.271. Our case of P is 3.69. So we are going to determine from our pressure diagram our sigma sub 1 prime and our sigma sub 2 prime, which is 13.82 kilonewton per meter squared and 30.39 kilonewton per meter squared. Of course, we have to determine our P1, our force acting on the sheet pile, which is now 153.36 kilonewton per meter. Of course, P is, we have to identify just so for the areas of area 1, area 2, and area 3. You have to divide those into section, the pressure diagram. So you can identify now your Z bar. So using the equation that was presented a while ago. So that is Z bar is 3.2 meters. And you have this equation, or simply you have sigma sub 6. You try to get the value for sigma sub 6, which is 51.86 kilonewton per meter squared. So once you have your sigma sub 6, you simply have to substitute to this equation so that you can solve for the theoretical depth of penetration, which is 1.6 meters. And from the force of the anchor rod equal to this equation, and that is now equivalent to 70.38 kilonewton per meter. For anchors, for the anchors, the general types of anchor used in sheet pile walls are as follows. We have the anchor plates and beams. So you have here the anchor plates and beam. You have the tie box. You have the vertical anchor piles, and the anchor beam supported by batter or compression piles. So if you're going to observe, you have here an anchor plate or beam, which is basically made of cast concrete blocks, and they are attached to the sheet pile by a tie rod. So a rail is placed at the front or back face of the sheet pile for the purpose of conveniently attaching the tie rod to the wall. So we have here a concrete grout. This is attached to the sheet pile using a tie rod or cable. Same thing with this, you have an anchor pile which is attached using a tie rod. And for this one, you have an anchor beam. It is also attached using a tie rod attached to the sheet pile. So those are various types of anchoring for a sheet pile walls. So the holding capacity of anchor plates in sand, according to Ovisen and Stallman, proposed a semi-empirical method for determining the ultimate resistance of anchors in sand. So we have here the steps in the calculation. So for the basic case, for the step 1, determine the depth of embedment h. You have to identify this value h. Assume that the anchor slab has a height of h and is continuous. For example, b is equal to the length of the anchor slab perpendicular to the cross section, which is equal to infinity, as shown in this figure. So we are going to have this. We have to be familiar with this notation. To compute for the ultimate resistance per unit length of anchor for P sub u prime, you have this equation, and if we try to simplify, this is now your equation to compute for the ultimate resistance per unit length of the anchor. So you have to obtain the value for K sub A, the active pressure coefficient, and the passive pressure coefficient. So to obtain our K sub P cosine delta prime, you have to calculate first K sub P sine delta using this equation. And for step 2, the strip case, determine the actual height h of the anchor to be constructed. If a continuous anchor, for example, an anchor for which b is equal to infinity of height h is placed in the soil so that its depth of embedment is h, as shown in our figure 9.34. So the ultimate resistance per unit length of the strip case is, you have this equation. You have to take note that C sub OP is equal to 19 for dense sand and 14 for loose sand. So for the strip case, you have this. You have this, the vertical anchor. So to compute for the ultimate resistance for the strip case, you have this equation. So step 3, actual case. In practice, the anchor plates are placed in a row with center-to-center spacing S prime, as shown in figure for this one. So this is the actual case for the actual case for the anchor. For this actual case, of course, the anchor are spaced at a certain distance. We denote that that's S prime. And to compute for the ultimate resistance of each anchor, you have this equation. Of course, B sub B is the equivalent length. And we have here the correlation, empirical correlation based on the model test conducted by Gali. So for the ultimate resistance of a single anchor, this equation can be used. So according to Gali, to develop a load displacement relationship for single anchors, we have this relationship. P all over the ultimate resistance per unit length of the anchor is equal to 2.2 times U, the horizontal displacement of the anchor, at the load level P over H raised to 0.3. So for the factor of safety of anchor plates, you have here the equation. And for the spacing of anchor plates, this is the equation that you're going to use. Allowable P all, which is the allowable resistance per anchor plate all over the F, which is the force per unit length of the sheet pile. So we have here a sample problem, a row of vertical anchors embedded in sand shown in this figure. The anchor plates are made of 6 inches thick concrete. The design parameters are B equal to H, which is 1.5 inches, and S prime is 48 inches. Capital H is this one is 37.5 inches. Our small h is 15 inches. Gamma is 105. P is 35. The unit weight of the concrete is 150. We have to determine the ultimate resistance of the anchor plate. So we have to compute for W. So we have this equation, H times the thickness of the plate of the anchor plate times the unit weight of the concrete. That gives us 234.4 pounds per feet. Then simply have to compute for K sub P sine delta prime, so that when you have this value, P prime is 35 degrees, the magnitude of K sub P cosine delta prime is from figure 3.33, that is now equivalent to 4.5. Now you can compute now for the ultimate resistance of the anchor rod. So using this equation, it gives us 2,198 pounds per feet. Your P sub US prime, we assume that the sand to be loose. So we have this equation. Our C sub OP is equal to 14. Substituting that one to this equation, we have the value for H. We have the value for small letter h, that gives us 1,998 pounds per feet. And of course, we have this one can be solved, and that gives us this ratio is 0.63. And for this equation, which is equal to 0.63 and loose sand, our figure 3.35b, you have this expression which is 0.227. You can compute for B sub E, the equivalent length, which is 2.24 feet. And from there, you can now compute for the ultimate resistance of the anchor, which is equivalent to this equation. We have computed that one, 1,198 times 2.24, which gives us 4,476 pounds. So this is an experimental variation of the values for P sub U all over HB times C with H all over H for a plate anchors in clay. So for the ultimate resistance of tie backs, if the tie back is in sand, our ultimate resistance is equivalent to this one, pi times D times the L times the average effective vertical stress, K, our earth pressure coefficient times tangent alpha prime. And of course, if that is, of course, our L is this one, this is our D, and of course, the distance from this top towards this one is our Z. If the tie back is in clay, the ultimate resistance is given by this expression. Of course, our C sub A is equal to adhesion. So that ends our discussion for sheet pile. So I hope that basically, if you have questions, you may ask questions.